of our speaker today, Elliot Duff, Principal Research Scientist, Mining Robotics at CSIRO. Elliot's main focus has been in the area of field robotics and the deployment of autonomous machines in hostile and unstructured environments. Elliot currently leads CSIRO's real-time perception project. He will speak to us about mining in the cloud.
Good morning. Okay, presentation on mining in the cloud. This is a presentation about what the experiences I've had over the last 15 years in mining robotics and where I think things are heading, or where we'd like them to head. And so I'll introduce, I work for CSIRO. CSIRO is Australia's premier research organisation. It's about 6,000 people, about $1 billion of cash, of which about 60% is from the Australian government, the taxpayer, and then the rest is from your good sellers and some other operators and vendors. And so we've broken up into a number of different flagships that address different sectors of the Australian economy. And in this particular case, it's the Minerals Down Under flagship. So here's the story. Basically, the presentation is about where we started from back in prior to 2000 and where we're heading to in the future. And we split this presentation up into the stages of what we think automation, the stages that will lead to the mining in the cloud, and some of the technology that will facilitate that. So let's start. So CSIRO in the mineral sector, we have possibly about 500 full-time researchers that are working in this space. And everything from exploration, production, planning, through to rehabilitation. And all the other different decision support and visualisation. And so if we look at traditional mining, if we break it down into a very simple process, what we have here is one mine called M1. This is my maths background. With a number of processes that are involved, and we have an operator or a mine manager that operates that process. And for reasons of safety, and this happened more than a decade ago, what we tried to do is move some of the operators away from the machinery. And to do that, we needed to build in systems into the machines that prevent the machine from self-harm, and also we need to improve its performance. Remote operations often degrades the performance of the vehicle. And we need to also reduce the levels of operator input. And see some of the technology, so there's GPS obviously, LiDAR, vision, haptics, all different, and robotics technology. That's all the technology that supports that. An example of the project that came out of that is the LHD automation that we're involved with Caterpillar, with MineGen, and it's similar technology to Sandvik and Atlas Copco. And so effectively what we do is just move the operator off the vehicle to some local remote control station. And also we've been involved in underground in the automated longwall. That's my colleagues in another division. And so what are the issues? So what have we learnt a decade ago? Well, the first thing we learnt is that it takes a lot longer to automate something than you think. So we basically demonstrated an autonomous LHD at North Parkes in less than 9 months. 10 years later, we have a product. And the reason for that is to get through the regulation and to get through all the safety issues. There are a lot of issues that need to be solved. So the technology is 10% and the 90% is the development. So that's the first rule. The second rule is, or the lesson that we've learned is that by automating a piece of equipment, you may have reduced the hazard to that person, but you may have increased the hazard to bystanders. So the issue in all these environments is that we have to segregate or isolate all autonomous vehicles from people. And this is a big challenge because it can have impacts upon productivity. So what have you gained by automating a piece of equipment? You may lose in maintenance and other areas because the fact that people and automated machines can't mix. So that needs to be really understood and may need to change the way that you operate your mine or the actual workflow that happens. And And the other lesson to learn is that when you decide on a level of autonomy, it's very important that you choose the type of user interface that controls that machine. And effectively what we're doing is saying when we pull people away from machines, we need to use technology to bring them back together. And the nature of that technology will depend on the levels of automation. And so in this case here, if you have assistive automation, then it's appropriate to use what we call augmented reality, which is like your VO feed with data. But if you're in a supervisory mode, then you want something more like augmented virtuality, which is more your cartoon. And the reason why you do that is because you need more situational awareness when you're in a supervisory mode that a single video camera doesn't provide. This is some of the lessons. Okay, so this is where we are from a few years ago, and obviously Rio's involvement here in the Remote Operations Centre. So what we've decided to do here is, as well as moving people away from the machinery, let's put all these people in a single Remote Operations Centre so they can all communicate and talk to each other. Now the challenge here is that we start to need to look at cognitive situation, because effectively what we need, these people are operating multiple machines in different areas, in different lines. We need to look at the cognitive load of these people. So what we need to look at is more sophisticated user interfaces. And here's an example of those, things like augmented virtuality, which I mentioned, domes, haptics, decision support systems. These are all the things that will assist in those remote operation centres to improve the productivity. And so then we lead to the next step, which is the concept of remote mining services. Because what we've done is we said, well, if we can move everybody to a remote operations centre, does it make sense that one person is in charge of one mine? Or can we cut and dice it so that, say in the case of a rock breaker, then the operation across the whole Pilbara can be operated by one or two companies that break rocks. So the idea is to moving to a service model rather than a sort of production. Now, if we do this, we need to. There's a problem of a blame game here. Somebody's going to say, "Well, I've dealt with my system; it's your problem now." So what we need to do is look at better communication standards and more situational awareness in the mine, in this remote operations centre. And one of the key things is geological awareness. Now, when we really understand the issue here is if we want fully autonomous mines, and if there's no one there, you've really got to understand that there will be no one there. And that means there won't be conversations in the tea room about the state of some rocks or some road conditions or the bench. There won't be those conversations happening because everybody's going to be in this control room. And so what we need to do is fit our machines with a lot more geological awareness. The awareness that humans have or geologists and surveyors have has to be put into the machines. And so that once we have that geological awareness, then we can move to a model which I call mine virtualization. Effectively what we've done is we put the whole mining operation into a cloud service. Now, I'm not talking about, Dropbox or something like that. It's going to be a private cloud, but the idea is that different people, different agents will have access to this mine through different portals. And what the idea here is that the mining company will run a mining business centre rather than a remote operations centre. And the operations can be sort of cut and diced in different directions. And it's the data in your infrastructure that is the business now of the mining company. Now, to do this, it's critical that we have information flow. And in fact, what's going to happen is the flow of information is now going to be as important or more important than the flow of ore. If the information stops flowing, you won't be able to mine. And so what we have is in the current situation is we look at the current mining process. The communications between each process are very ad hoc and bespoke. What we would like to do is move to a more general system where we have a common data framework, a common mine communications infrastructure across the whole mine, so that every process can talk to every other process. For instance, some geological sensor on an excavator can report on the fragmentation and the ore grade, which then can be fed back into the block model and so forth. You get these feedback loops, so you can optimise your whole mining process, not just one. So we see it as a whole of mine optimisation. And what is required here is effectively 4 people who wish to access this data set, we need a directory service, and we need a common mind model so that people understand the contents or context of the data that they're asking for. And this allows us to then do simulations in the future about different supply chains and so forth. And in the IT world, what this is basically about is creating a digital world, a digital version of your mind. So there's the real world, there's a digital world. And in this digital mind world, everything that happens in the real world gets replicated, and everything you ask to happen in the digital world happens in the real world. There's a mirroring, it's called mirror worlding. And this is happening in other industries, and it's an interesting area of research at the moment. It's part of these mega trends that are happening. So that's the flow there. Now, so we're looking at this mind virtualization or mining in the cloud. What are the risks involved? So if we go look at some risks. Well, the real risk here is how do you guarantee the performance of the mining process when there are no people there? How do you do that? Well, the first thing is you need to sort out machine dependability, and we've done some work in that, and other people are working there. So that's one problem. And the other one is machine intelligence. And this is a challenge for the robotics community. So what we normally do in robotics is we do what we call biomimicry. We look at the human or the animal kingdom for different types of models for robotics. And in this case, we look at a traditional miner. And what is required in this is what they call strong AI, basically to get an intelligence system that replicates human intelligence. Now, the problem with that, well, what that requires is a private world model. In the head of the robot, you'll need an understanding of what the mining world is so that it can make intelligent decisions. The problem with that is that the positronic brain doesn't exist yet. And the AI community aren't sitting there saying, if only I had more computational speed. At the moment, they're saying, if only I had better algorithms to sort this out. So there's a risk there that we may not solve that problem. So the other one is biomimicry of the insect, and that's called swarm AI. Now the problem with, swarm AI has no world model, it just has behaviour. And the problem with that is that you get emergent behaviour out of the system. So if I told my swarm robots to go and get gold, there's nothing really stopping it from removing it from people's heads. So you can see where there is a problem with swarming behaviour, because it's very hard to guarantee the safety of the environment and so forth, and people. And there, of course, there's some science fiction about that one. So let's look at what nature didn't invent, and let's not go for biomimicry, and let's look at the internet. I mean, nature didn't invent the internet, and didn't invent wireless comms. Actually, we did, but that's another issue. So what's happening here is, this is happening in Google and other areas. It's called collective intelligence. The internet, there's arguments that the internet's actually going to become intelligent, that it's going to become aware. And it's happening because all this analytics are happening on huge data sets. It's called big data. There's Microsoft calling it the fourth paradigm of data collection. And so this is where we see the future of intelligent machinery. And what we're really doing is saying, instead of each machine being intelligent, we make the whole system intelligent. And what is required there is a shared world model of the world. And the idea is that each robot interacts with that. And of course, this is the common mind model that I was mentioning earlier. And so the risk for this technology is that we need ubiquitous computing, which is always connected, always aware. And this is achievable with our mobile telephones. This is where technology is heading. Okay, so that's the robotics side. The other issue about automation or any technology is you need to understand the doctrine. You need to change your doctrine. With technology, there's no point in doing the same process with this new technology. It's important to reconsider how you mine. And so, examples of that are some work we've done called ROSE, Rapid Ore Extraction. But the work that I've been involved in is SLAM technology. And so SLAM is called Simultaneous Localization and Mapping. And this has been in robotics for about 12, 13 years as a theoretical concept. And it's something that we've been involved with in mining. And what it effectively does is says that we can map the environment, in this case with LiDAR. So basically time-of-flight lasers measure the environment. We can map the environment and tell you where the machine is simultaneously. Now this sounds like a little bit of a free lunch, that you're getting something for nothing. You can either get a map or how do you get both? Well, the reality is that you can do it when you walked into this building. You've built a map of of the venue here, and you know where you're sitting, hopefully. And you've done that without GPS. You've done it with a poor vision sensor and poor inertial sensor. And you can do it through software. So we're trying to replicate that same behaviour. And an example of that, we went to North Parks last year. Now, North Parks was very interested in finding out, they wanted to fit some equipment down their mine. And they needed to know the three-dimensional shape of their tunnel very quickly. So this is a bit ugly. It's that laser system there, there's two lasers in a trawling configuration and one in a spinning configuration. That was designed for doing some experimental work in a corridor, and we just wrapped it in plastic and stuck it on the back of the ute. And here are the results. So you can see the tunnel. So what you're seeing here is the laser goes through, creates a point cloud. We convert the point cloud into a surface, and then we run it through an animation engine just for your gratification, so you can have a look at what's going on. And so the light is not a real light, it's all an animation. But the data that this animation has been created from is real. Now what's significant about this is that we're able to map 17 kilometres of the decline in 2 hours. So that machine, the laser was bolted on the back of a ute and driven at 30 kilometres an hour with other traffic. Now this has significant impact. If we can map a mine in 2 hours, then it changes what we can do with maps, because you say, well, if I can just stick this on a ute and map it in 2 hours, why don't I do it every day? And if I do it every day, then I can start looking at change. What's changing in my environment? And this is a very important thing for automation, because automation currently doesn't deal with change very well. And we need to understand what change is. Change is one of the best indicators for collision detection, for instance. You know, when you're driving on the same road day after day, if something changes, there's some erosion or something on the side of the road, you'll slow down. We then took this same system to Jenolan Caves, and this is the map that we took from Jenolan Caves. So we mapped 9 kilometres of this in 10 hours. The last map took 20 years to build. Now, this current system here was a big, heavy laser with a battery on a tripod, and we had to abseil it down. Now, nothing motivates researchers more than inconvenience. So they said, look, there must be a simpler and lighter way to do this. And so we developed a handheld version of our LiDAR system. And this is it here. And it should have smoke coming out the top, and the guy should be chanting, but... so what it is a small, custom, commercial off-the-shelf LiDAR that has a range of about 30 metres and has a resolution of a centimetre. And the idea is that it uses human motion to passively actuate it, so it nods. So we don't need batteries, we don't need motors to drive it. And from that, we can build maps in real time of the environment as you're walking around it. And by the way, it loves stairs, so it doesn't have the problem that some other machines have. So that changes the whole paradigm of mapping. We can map a building in the time it takes you to walk around it, and that can include a mine or a processing plant, anything. So to finish off, so what we're really interested in this future, going forward towards this mining in the cloud, is moving from a mining culture to a mining services culture, where we provide services into those clouds.